All right, we had some questions about the latest lesson that we have been assigned on Cognity. So I'm going to start with some definite integrals and then go through some of their applications, which is what you guys are seeing this week. So finding area under curves or area between two functions. And then that'll eventually be extended into finding volumes of solids created by taking those areas and revolving them around an axis. So in our class, we just focus on revolving around the x-axis, but in other calculus classes, you can revolve around different axes. So I just want to talk quickly about a couple different, problems that you might have seen. So keeping in mind, we now have a new definition. So before we saw the integral symbol with a function that represented a derivative. So now we are seeing that, but with a upper and lower boundary. So this would be like from A to B. So it's just telling you on the space of an x-axis how much space to find the area under the curve represented by whatever f of x is here. So I'm going to start easy. Let's say we had this nice easy function. So what is this saying? It's saying if we were to look at this function on a graph, how much space is being taken up by this function. And by definition, what we're saying is you can anti-derive the function and then use the fundamental theorem of calculus to figure that out. So what is the antiderivative of x minus 2? So it's 1/2 x squared minus 2x, and we take that from 0 to 3. So the fundamental theorem says we are substituting in these values, so it would be 1/2. Our first x value would be the upper boundary, 3 squared minus 2 times 3. And then we subtract the value of substituting in 0. In this case, that would just end up giving us 0. So we would get 9/2 minus 6 minus 0, so negative 3/2. So I want to talk about what that means whenever we have an answer that is negative. So hopefully in your reading or in your practice you've noticed if this is representing an area under a curve, then if it's a negative answer, then either the area, all the areas underneath the x-axis or the majority of the areas underneath the x-axis. So I just want to show you what that means graphically. So I don't have any graph paper. Oops, I was doing matrices last. So if we put in this function, so x minus 2, and we go, let me reset this. All right, so I'm going to calculate. So if I choose my choice 7 here, so choice 7 is an integral, so see how it asks for the lower limit, 0 to 3 to my upper limit, and then it's going to give me some shading. So if I zoom in maybe for you guys a little bit. And so what's happening is, okay, let's try this again. Okay, second, I got a text, I got distracted. So 0 to 3. So you can see the shaded part is what the answer is representing. So because there's a bigger shaded part that's below the x-axis, that's why our answer is negative. So sometimes you're asked to find a total area. If you're asked to find a total area, you would find the absolute value of this portion. So you have to break it into little pieces. So just a quick review about exactly what we're doing. So the hard part about these is the anti-deriving, because sometimes we get a little bit confused on the rules. So all we're doing to find the area under the curve is exactly these steps. So I don't know if any of your cognitive questions, I should have looked at them before I did this video, but I did not. So I'm not sure if any of them ask for the total area, but just keep in mind what that means. You're just using the absolute value of the negative portion. So, all right, the next thing I want to talk about is the area between two curves. And I didn't really come up with a way to talk to you guys about this. I do have a textbook that I brought home to, maybe I can project that, I guess. So the area between two curves, this is an investigation. Let's see what we've got here. I just can't, I don't have any graph paper and I don't feel like sketching these. So, so here's an example of one of these. So example 12. So find the area of the region bounded by the curves, and it gives you two different functions. So sometimes you'll have access to a calculator, sometimes you won't. So this one's saying you wouldn't have access to a calculator. So if you think about the two functions that are being graphed, essentially the important part is understanding which function is on top of the other one. So that which one's going to enclose the area on the top versus on the bottom. So if this is a parabola and a linear equation, you can easily sketch these ones out. So you can sketch a parabola and sketch the linear function to see where the bounded area is. Now the process for solving a problem like this is you need to know where the area begins and where it ends. So the easiest way to do that, and you have to kind of harken back to your algebraic skills from when you were little babies, is just set those equations equal to each other. So if we set 4 minus x squared equal to x plus 2 and then solve it, oh, they did it. Oh, I could just be showing you this. So, yeah, so they set them equal to each other and they solve the equation so they get the two x values of where these two functions are meeting each other. So that's where the two x values are. So those are going to be your boundaries for your definite integral. So the order that they wrote these equations in is important. So you need to know which one is the top and which one is the bottom. So if we go back to that image over here, you can see the parabola. Oops, the parabola is enclosing the area on the top, and then the linear function is holding it on the bottom. So when you go to find the area between two curves, it's always the top function minus the bottom function. So you do that before you apply an antiderivative. So you would subtract these functions before you apply the antiderivative. So then you do the antiderivative and you do your fundamental theorem of calculus, and you can end up finding the answer that way. So this one ends up being 9/2. So if you're allowed a calculator, you still need to find where they intersect. So looks like the next one we're allowed to use a calculator, so let's take a look at it. So if we have an exponential function and a linear function, and we're looking to see where these two graphs meet, so what you would do is just type, you could type them both into your graph at the same time, right? Or so y1 and y2. Let me just show you what I mean. So e to the 2x plus 1, and our linear function was x plus 4. Okay, so let me reset my window. And again, you're looking for what's on top and what's on bottom. So now I see my top function and I see my bottom function. Oh, duh, you guys can't see that. My bad. So if you can you see it? So you can see that linear function is bounding the area on top, and then that exponential function is swooping down below. So it's important to identify top versus bottom function. So now we know when we go to set up the area that it should be the linear function minus the exponential function. You also, remember, need to know where these two functions intersect. So because I'm allowed to use a calculator, all I'm going to do is utilize the functions on my calculator to do that for me. So I want to know where these two graphs intersect. So is the function on the first curve? Yes. Is it now on the second curve? Yes. Hit enter. So it gives you, so this would be the upper boundary, right? Because it's to the right of this one. So there's my upper boundary. And you can see, what did I type in wrong? Oh, I see. That plus 1 goes, okay. I mean, we could have just solved that one, but duh. All right, let's see if, okay, so the linear is still bounding the top. Okay, so now when I go to find my intersection, beep, boop, beep. Okay, so that's still my upper boundary because it's to the right, but now I should have the same answer that they do. I do. Yay, nailed it. All right, so then how do I find the other point? I do the same steps, but now I'm just, when it asks me about my first curve, I'm going to scooch on over closer to this point of intersection, just using my arrows, and then do my enter. And then it'll give me the lower boundary. So you can see I have my two, my A value and my B value. And so now, to find the total area, I would go back to this, my y equals, and I don't need the first function anymore. There's obviously other ways you can do this, but this is what I do. And is it the best way? Who knows? I'm sure one of you can tell me a better way. And then I did my top, that linear function, minus my bottom. It was +1, right? Yeah. Okay, and then if I go to graph that, and then I go to do my antiderivative, lower limit are those two values, so I would have written them down because I'm a smart lady. I didn't write them down, but they're right here. So my lower limit was negative 2.998. My upper limit is 0.6469. And hit enter, and you can see it's going to shade it. And it ends up giving us the exact same answer as if we would have calculated it the old way if we were to sketch it and then do it this way. So it's pretty simple to find the area under a curve or the area between two curves. So being able to utilize your calculator is really important. But also being able to do these by hand. So on your IB exam, I'll send you some practice questions, or we'll probably just do all of this when we return from this lovely, lovely break that we have. But we will go back over all of this because there's some really cool things that we're kind of missing here by not being together. So if you were in the Zoom session today or you heard about the Zoom session today, we're going to go ahead and cancel the scheduled Zooms. And if anybody needs additional help or has questions about stuff, I'd be more than happy to Zoom with you in a private tutorial, or if you have a couple of friends that have the same question and you guys all want to meet up on a Zoom session at a time that works better for you, I'd be happy to do so. I can't send videos over Remind unless they're on my YouTube channel, so I wish I could do that because I could just knock out a tutorial that way. But just reach out to me if you guys have questions. I can do a full lesson, again, on any of these calculus concepts, but essentially we're always going back to derivatives or antiderivatives, and then there's going to be some application of those. So, I miss ya, and I can't wait to see ya, and yeah, that's it. Okay, bye.